Today's lesson is on the mean value theorem for integrals. We have a mean value theorem for derivatives, and then we're also going to talk about the second fundamental theorem of calculus. Before we get to that, we need to know how to find the average value of a function over ab. So this is going to be 1 over b minus a times the integral from a to b of whatever our function is, dx. So essentially what we're saying here is that if I have some function a, b, and it varies in its height, the average is going to be the entire area divided by b minus a, this distance here. Next is the max-min bounds of an integral. Okay, over a specific region, so b minus a, or b, a, b. So I'm going to illustrate this one, then we'll write down the rule. Okay, so let's say I have some function, and we're trying to find a range of values that are potentially represent the area under this curve. So we're looking at this whole area. Okay, so that would be the integral from a to b. Okay. The max-min bounds, we find the minimum. Okay, and no matter what, the area of this rectangle here has to be less than the integral area. So what would this area be? Well, it's going to be this distance, which is b minus a, times the height, which is going to be the whatever this minimum value is, which we're going to be calling little m. The maximum, we're going to take the maximum point on the graph, and the integral area has to be less than that rectangle. Well, the area of that rectangle is going to be b minus a times that y value, which we're going to call capital B, or capital M. So it's the integral area is in between the area of this big rectangle and the area of this little rectangle. So if little m is the minimum, and big M is the maximum, then the little rectangle, which was m b minus a, the area of that is less than or equal to the integral from a to b of f of x, which is less than the big rectangle, which was big M, times b minus a. Which leads us to the mean value theorem for integrals. So if f, our function, is continuous, there's always that caveat for most of these, there is an x, we're just going to say x star, it's a little star, where a is less than or equal to x star is less than or equal to b. So there's some x value in between a and b for which the integral from a to b of f of x is equal to f of x star b minus a. So I'm going to go back to my picture. So we already established that the integral area is somewhere in between the minimum rectangle and the maximum rectangle. That means that there's some other rectangle in between these two, so maybe like here-ish, where the integral area is going to equal that rectangle. This area and this area cancel out so that if we filled in that hole, this area would equal. Well, we're saying there's some value where the area of this rectangle, which would be the base distance here, which would be b minus a, times the height here, which would be the function evaluated at that x star, that rectangle area is equal to the integral area. Okay, and then looping this all together, the function value that is going to be used here is going to be the average value, and that should make sense that if I'm looking at the different heights, that the average value of this function times the b minus a is going to be the integral area. All right, so let's do some examples. So first, use the max-min inequality for integrals to find the upper bound and lower bound for the integral 0 to 1 of x plus square root of x plus 8. So we have our function. This is going to be the square root, move to the right. There's negative 8. So it's going to be like this. So this is going to be increasing. So from 0 to 1, this point is going to be my lower, this is going to be my upper. So 0, the y value at 0 would be the square root of 8. At 1, we're going to have the square root of 9, so it's going to be 1 and 3. So we're going to have m times b minus a is less than or equal to the integral from a to b of f of x dx is less than capital M, less than b minus a. So here my lower value is going to be root 8 times 1 minus 0 is less than or equal to the integral from 0 to 1 square root of x plus 8 is less than the big end, the maximum over that is going to be 3, 1 minus 0. So we can simplify this to this integral, whatever it is, we know that it is somewhere in between the square root of 8 and the square root of 9, which is 3. Okay, find the average value of 2x over 0 to 4. So average value is 1 over 4 minus 0 times the integral from 0 to 4 of 2x. So this is going to be 1/4 times x squared evaluated from 4 to 0 So we're going to have 1/4 of 4 squared minus 0 squared, so 16 divided by 4 is 4. So that is the average value. Now we're going to find the point where the average value, we're going to find the x where that happens. So we're going to set 2x equal to 4. So when x equals 2, we get our average value. Now we're going to sketch the graph of 2x over 0 to 4 and construct a rectangle over whose area is equal to the integral. Okay, So we're going to graph 2x. So there's the graph of 2x from 0 to 4. The rectangle whose area is going to equal this triangle at 2 there's our rectangle. So it should make sense that the area of this rectangle would equal the integral area from 0 to 4. Okay, find the average value of 1 over x squared from -1 to 3. So this is going to be 1 over 3 minus 1 times the integral from 1 to 3 of 1 over x squared dx. So this is going to be 1/2. The integral of 1 over x squared is a -1 over x, evaluated from 3 to 1. So we're going to have 1/2 times -1/3, which will be -1/6. And then minus negative, so this will be plus 1/2 times 1 over 1. So we get a common denominator. This would be 3/6. So 3/6 minus 1/6 is 2/6 or 1/3. So where does our function equal the average value? Okay, so where, and this is really our x star, but so we're looking for where x squared equals 3, which is going to be plus or minus √3, but on our interval here, we're just interested in the √3. And then we're going to sketch a graph. So 1, 2, 3. F of 1 is 1, and then it's just going to get smaller. So square root's going to be somewhere here-ish. So this rectangle equals the area under the curve there. Right, find the average velocity. So that's just another way of saying find the average value. So we're going to have 1 over 5 minus 0 times the integral from 0 to 5 of 32t. So this will be 1/5 times 16t squared, evaluated from 5 to 0. So this will be 16/5. I'll pull the 16 out, times 5 squared, which would be 25 minus 0 squared, so that's just going to be 0. This is going to give me 80. All right, so 2015, Joanna jogs along a straight path. For 0 is less than t is less than 40, Joanna's velocity is given by the differentiable function v. Selected values of v prime, where t is measured in minutes and v of t is measured in meters per minute, are given in the table above. We're going to use the data in the table to estimate the value of v prime. So we're going to have v of 20 minus v of 12 over 20 minus 12. Okay, so you can leave this just like this, or simplify. So this would be 40 over 8, which is 5. The units would be the top units divided by the bottom minutes. So this is going to be meters per minute per minute. Okay, then in part B it says, using correct units, explain the meaning of the definite integral 0 to 40 in the context of the problem. Approximate the value using a right Riemann sum. So from 0 to 40 of the absolute value of the velocity is going to be the total distance traveled. Because it's going to account, if we just had the integral from 0 to 40, it would include negative areas, so it would take out, it would be displacement rather than distance traveled. But with the absolute value, it's the total distance traveled from t equals 0 to t equals 40. Okay, then we're going to approximate it with a right-Riemann sum. So our width, the width of the first one is going to be 12. The height at the right end is 200. The next one's width is 8. Its height is 240 on the right-hand side. The next one's width is 4. Its height is negative 220, but we're doing the absolute value, so this will be positive 220. The last one from 24 to 40 is 16, and its height is 150. And we would leave it just like that. Then we have Bob. Bob is riding his bicycle on the same path. For time between 0 and 10, Bob's velocity is modeled by t cubed minus 6t squared plus 300, where t is measured in minutes and b of t is measured in meters per minute. Find Bob's acceleration at time equals 5. So if this is his velocity, we want to take the derivative and evaluate that at 5. So this gives me 15, and this again would be meters per minute per minute. Okay, based on the model B from part C, find Bob's average velocity from 0 to 10. So that's going to be 1 over 10 minus 0 times the integral from 0 to 10 of t cubed minus 6t squared plus 300. So this is going to be 1 over 10 times 1/4 t to the 4 minus 2t cubed plus 300t, evaluated from 10 to 0. So we're going to have 1 over 10 times 1/4 10 to the 4th minus 2 10 cubed plus 300 times 10 minus, if I plug in 0, 0, 0, it's all going to be 0. So there's my unsimplified answer. Given this was the equation, I would suspect this was a no calculator question, so you would just want to leave it just like that. All right, so that's how we find average value. We're going to move on here. Okay, we're going to evaluate the integral from 2 to x of t squared dt. So this is going to be 1/3 t cubed, evaluated from 2 to x. So that's going to be 1/3 x cubed minus 1/3 2 cubed, which will be 1/3 x cubed minus 8/3. Now I'm going to take the derivative of what we just found. So if I take the derivative of 1/3 x cubed, we get x squared. If we take the derivative of 8/3, we get 0. So the point here is if I integrate and then take the derivative, we end up with the same thing that we started with, just with this variable instead of this variable. So this is the fundamental theorem of second fundamental theorem of calculus. Says that the derivative of the integral from some constant to x will just be f of x. All right, so if I take the derivative from the integral from 0 to x of t over cosine t, that is just x over cosine of x. This one's the same function, but we've switched these. So if I were to switch this around, we would have ended up with the opposite. So this is going to be negative x over cosine of x. Derivative of the integral from 0 to x of dt over 1 plus root t is 1 over 1 plus root x. All right, these next ones, if you look, we have an integral from a constant to function. So we're going to add another rule up here, that the derivative with respect to x of the integral from a constant to a function, we're going to call this g of x, of f of t dt is going to be f of g of x times g prime of x. Okay, so going down to the bottom, this is going to be 1 over 2, instead of t cubed, we're going to have x cubed cubed times the derivative of x cubed times 3x squared. So that would be 3x squared over 2x to the 9th. And you don't have to simplify this, which would be 3 over 2x to the 7th. But you could just leave it like that. All right, let's do another one. So first thing, we're taking the derivative, but we have a function here, not just a x. So this is going to be x squared minus 3 over x squared squared plus 7 times the derivative of x squared, which is 2x. Okay, and these next ones, we have a function and a function. So we're going to add another one to the definition. Okay, to give myself room, I'm just going to write it right underneath. So the third one of these is if I have the derivative, and now I have g of x and h of x of f of t dt. All right, so we're going to have f evaluated at the top one, h of x, times the derivative of h, minus f evaluated at g of x times g prime of x. So it's just the chain rule. So this is going to be cosine x cubed times 3x squared minus cosine x squared times 2x. Here we're going to have 3 over x plus 1 times the derivative of x, which is just 1, minus 3 over negative x plus 1 times negative 1, or 3 over x plus 1 plus 3 over 1 minus x. All right, this one. For the limit, if I were to plug in 1, the integral from 1 to 1 is 0, and 1 squared minus 1 is 0. So this is 0 over 0, which means I'm going to use L'Hopital's rule. So I'm going to hit the derivative of the top and the derivative of the bottom. So the derivative of top is going to be cosine of x, the derivative of the bottom is going to be 2x. Now when I plug in 1, this is going to be cosine of 1 over 2 times 1, which is going to be 2. All right. So we have a function from 0 to x cosine t over t squared plus 3. F of 0 is going to be the integral from 0 to 0 so that's simply going to be 0 because the integral from the same thing to the same thing is 0. F prime, well that's going to be the derivative of this, which is going to be cosine x over x squared plus 3 evaluated at x equals 0, which is going to be the cosine of 0, which is 1, over 0 plus 3, which is 3. The second derivative, we're going to have to use the quotient rule. It's been a while. We have cosine x prime, x squared plus 3, minus x squared plus 3 prime, cosine of x, over x squared plus 3 squared. Okay, derivative of cosine is negative sine 2x cosine x all right, and we're evaluating this at x equals 0. So this is going to be sine x, not sine of x, sine times this. So sine of 0 is 0, so that's just 0. 2 times 0 is 0. Over the denominator gives me 3 squared, so this is 0. Okay, last question here. Let f be a differentiable function for all x. Which of the following must be true? That the derivative from 0 to 7 of f of x is f of x. False. This would just be a value, which means this would be 0. The integral from 7 to x of f prime equals up. No, this would just be f prime. Okay, d dx of 7 to x of f of t is f of x. That is true. That is the fundamental theorem. Second fundamental theorem. So that is the mean value theorem and the second fundamental theorem of calculus.